Okay, now, rewinding back to advanced functions. The first time I did end behavior, I subbed in big numbers and did that whole crazy table. Then we came up with a set of shortcut rules of what we were seeing in building those tables. And what I'm about to show you here is like an algebraic move that'll take all those rules and just put them on the shelf. If you get this, you don't need all that stuff. But this is difficult. This is sort of awkward what I'm going to do here. So I'm going to do it really slow and carefully the first time. This says, find the limit as x approaches infinity. It says negative infinity, but I'll deal with that when I get to it, okay? Sub in a big negative infinity number, and maybe we know what the answer is going to be in this one by the rules, but maybe we forget the rules. This trick I'm going to show you is not only for these type of examples. So if when I'm done you're like, I like the rules better, you might want to check out this rule because it does other things as well. We're trying to grow in the middle of this. And what I'm going to do is multiply by, again, my very favorite number to multiply by, the number 1. I've got to multiply with the same thing, top and bottom. Now, what I'm going to choose will be a mystery when I put it up there. When I first put it up there, go, how did you choose that? And by the end of the example, you'll go, I know how you chose what you did. Yeah? And then we'll know for other ones, okay? This works for finding limits at infinity. I mean, that's the name of this lesson, finding limits at infinity. So what I'm going to multiply by, and actually through the whole example, you can think about how I made this decision about what I'm going to multiply by. I'm going to multiply by 1 over x squared on the top and 1 over x squared on the bottom. It seems like a really extreme choice, but it's going to do great stuff to this thing. It's going to put it in the perfect form for finding limits at infinity. So, this doesn't change, limit as x goes to negative infinity. Essentially, every term in the numerator and every term in the denominator is going to get put over x squared. So 8x squared gets put over x squared. 7x gets put over x squared. 5 gets put over x squared. And in the denominator, all the same. 2x squared goes over x squared. 9x over x squared. 1 over x squared. And at first glance, you're unimpressed because you're like, all you did was make things way, way, way more complicated. And still your brain's bouncing around and going, how did he choose x squared as the one he was going to use? And you'll see, by the end, you'll see why I chose that. Let's look at the individual terms because apparently something's up. I'm up to something here. Check out the first term. Just focus on that for now. 8x squared over x squared. The x squareds cancel, and I've got the number 8. And if you thought things were worse when I multiplied by 1 over x squared, they were worse until this canceled, and now things are better. The number 8. I can deal with the number 8. I know all about number 8. Next one, 7x over x squared. Only one of the x's cancels, and I get 7 over x. Here, nothing cancels, and I get 5 over x squared. So some of the terms got down to just numbers, and some of them were left with x in the bottom, which again, you're unimpressed. You're like, it's still a giant mess, Mr. Todd. Like, this is worse. On the bottom, 2x squared over x squared. The x squareds cancel, and I get 2. And I get 9 over x, and I get minus 1 over x squared. That's the only algebraically difficult step. So if there's a problem there, you need to tell me now with what I just did. Is there a problem with the moves I've made? Oh, it's starting to happen. You're starting. I don't ask much during the lessons. You sit there, I'll provide all the energy, but a little bit of nodding or head shaking goes a long way to help me know what to do next. Now check this out. I argue this thing's perfect now for finding limits at infinity. There'll be no problem finding this limit at infinity. Let's do them each individually. Because remember, limits are well behaved. I can find the limits individually, add and subtract them later. I can do whatever I want. The limit at infinity of 8. It's 8. It's always 8. I mean, you don't have to worry about numbers like that. Let's talk about 7 over x. We really need to get this. It needs to be like perfectly clear. If I sub in really big numbers and getting progressively bigger, 7 over 100, 7 over 1,000. Oh, okay, sorry, they're negative. Like that matters. Here. Sub in negative 100, 7 over negative 100. Then I go negative 1,000, 7 over negative 1,000, 7 over negative 100,000, 7 over 1,000,000. what's going to happen to that part of this thing? What's it going to head towards as I keep dividing by big numbers? I don't mean not just big numbers. The biggest numbers. Bigger than the biggest numbers. Big, big numbers. What's this going to become? 0. If you're with me, the next line is this. Huh? Everything that had x's in the bottom of any description became 0. Numbers just stayed where they were, and things just got a lot better. It was a lot worse for a while, and then it just got a lot better. Technically, I guess if I'm subbing in negative infinity here, this would be a positive 0. Like that particularly matters in this example. It doesn't particularly matter because plus 0 minus 0. This one would be positive 0. This one would be negative 0. So if somebody's really with me and they're like, wait a minute, this says negative infinity. I'm just trying to show off that that really doesn't matter in this particular example because positive and negative 0, same thing. And what I get is your rule that came from advanced function, which is the degrees were equal. So I do ratio of the coefficients equals 4. Now, if that was just all that work to replace your one little rule, it wouldn't be worth it. But it does other stuff. This particular move and this brand of moves is too powerful to ignore. And if you hated the rules, you're like, I don't want to watch the old advanced functions rule. You don't have to now. This will work. It will recreate all of the rules that came from before and do other things. Yeah? It slices, it dices, it makes dinner, it does everything. So it takes care of your old stuff and it does some new stuff. If it looks like a lot of steps, it's not. It's just because I was teaching it that it's this many steps. Most people do this in 2 steps when they get good at it. I'll keep doing it in lots of steps. When you go to do it, you're going to be like, boom, boom, done. Now, all that time, where did I get the 1 over x squared from? How did I choose that? It's the biggest one. Just find the biggest one. Make sure you cancel out the biggest one and everything else will happen. Yeah? Well, I'm not sure what you want to do here. I think the easiest way to handle this mess when they've given you 2 separate terms like that is just to use your limit laws and go, you know what? I'm not going to try and get these 2 things together. I'm just going to use limit laws and go, okay, limit as x approaches infinity of 8x over 2x squared minus 1. And I know what's about to happen, so I'm going to leave a little space there because I got to do something to that thing. And over here, I'm just going to go, yeah, minus limit. I hope I left enough room here. I really went over here because I'm not particularly worried about this limit. I hope you're at least far enough that this limit, no problem. So now let's see, let's check in with you if you like my new trick, because again, if all those rules confused you earlier, you don't need them if you really get this trick. What would you like to do to this thing to make it better for finding limits at infinity? It's not better. It's not better just walking down the street better. It's better when you specifically are trying to find limits at infinity. What would you like to do to this thing? Josiah. Multiply by 1 over x squared, and I think he knows what he's talking about. I'm just going to add a couple of words. Multiply top and bottom by 1 over x squared. And maybe he said that it's really hard. Boy, I'm glad I got the microphone. It's shocking how hard it is to hear you guys with your math on. So I'm going to do this another color so you can really see what's happening. Multiply that by 1 over x squared. It was just a coincidence that this one was x squared as well. Okay, so I don't want you to go home thinking, oh, we always multiply by 1 over x squared. No, 1 over the biggest x power you see. So I'm going to tidy this up pretty quickly, not to rush you, because I don't know if you've noticed, I really slowed it down. I'm out of rush mode. This is all I'm teaching today. Then you got the rest of the day to get organized, and we'll try again tomorrow on the 3-lesson plan, and we'll see if we get there. I'll do this fairly quickly this time. I'm going to sort of skip a step. And just tell me if it's no good that I skipped a step, and I'll try and fit it in there. Just to prove that this goes faster than what I showed here. Yeah, and it can compete with the 3 rules. Give that a stare and let me know if you think, yeah, when I actually go to do it, that's what I'm going to do. I don't necessarily have to write them all over x squared. I know what's got to happen here, and I'm good enough at my algebra now that I can cancel as I go. If you're not, do the extra step a couple of times. Great. And then after doing a few of them, you'll practice enough to go, okay, I got it. I don't want to get sidetracked here, but I see a couple people reaching for their head. Unlike regular school, you're going to have to take care of yourself better, folks. Like, on the break, I ate, and I drank a whole thing of water and half of another one. Yeah? You're just going to have to get better at eating and drinking and exercising and sleeping and all those things to get through this. It's like boot camp for university here. Any complaints about this? I argue it's really set up for finding limits at infinity. It's not better. It's a big mess in comparison, but it's ready for limits at infinity. I can do them each individually. We found out limits are friendly. I can do the limits of the numerator and divide it later. I can do the limits of these individually, no problem. As x goes to infinity, what's the limit of 8 over x? 0. That part has to be like, yeah, I totally get that. And in fact, I can still remember from, I'll put it in a separate box here. Oh, I'll put it up here. I still remember this from a university lecture pack as one of the fundamental limits they told us to memorize, and this was it. Limit as x goes to infinity of a over x to the n equals 0. Basically saying, doesn't matter what number's on top, if you've got x to the power of something on the bottom, and you're going to infinity, that term's going to 0. Powerful little limit, but not complicated. So I get 0 on the top. I get 2 minus, how about 1 over x squared? 0, even more 0, yeah? 0 is 0, yeah? And then over here, minus, okay, limit as x goes to infinity of 7. So unbelievably easy, it's difficult. Look at this one carefully. 0 over 2. I want to talk about that for a second. It's one of your 3 rules for horizontal asymptote. Before, you would have said, oh, degree of the numerator is lower than the degree of the denominator, so the limit, the horizontal asymptote, is 0. This handles that. It does all the rules built in. Yeah? I got a secret for you. If you had been here for advanced functions in class, I would have showed you this. In class, we would have had time for me to go, listen, if you don't want to memorize the rules, let me show you this. At that point, it might have been too much for you, too much algebra for you, and you might have memorized the rules. But this is the alternative to the rules. 0 minus 7 is negative 7. You can always check these in your calculator because you can just take this thing and sub in x equals 1,000 and see what you get. In this particular case, you'd get negative 7.01 or negative 6.99 something. You'd go, oh, negative 7, looks good. It's not going to be exactly negative 7. It's heading towards negative 7. I saw a hand there and I talked over it. Who was it? Or I explained it? Did I? We're good? Any questions there? What's that? Lots of that's going to happen in calculus. He suggests that this seems almost too easy sometimes, as we're getting to know it. And that's going to happen in calculus. That is the beauty of calculus overall, is that as we go through, there's going to be moments you're like, that's all I got to do? Yeah? And it's really going to be a test of your algebraic skills. If your algebra is good, the ideas of calculus are very, very nice. Okay? This one's different. Why is this one completely different? I tried to say it every time I went through it about why I was doing what I was doing. Let's rewind. What did I keep saying about what was nice about this form? It was ready for something. For x approaches infinity. So this is a specific x approaches infinity example. Now we switch gears. This says as x approaches 4. Worse, it's x approaches 4 from the positive side. What is going on? Well, there's lots of information to know, about what's going on before you can really address this question. First, this thing has a vertical asymptote. At x equals 4. So what they're asking in the question is, here comes the vertical asymptote. Draw your vertical asymptotes with a dotted line to say, hey, the graph can't go past this. It approaches this. But what this question's asking is, how does it approach it? As you come in from the positive side, from this side, as you come in from the right side here, does the graph go like this? Or does it go like this? That's the question. And in advanced functions, we pretty much had to do all the other work. We graphed the whole thing. And eventually, we deduced what was going on here. This is asking directly, what are we going to approach this asymptote this way or that way? And I want to push forward just a second before I answer a question here is, the answer's got to be either infinity or negative infinity. Yeah, it's going to infinity one way or the other. The question is it positive infinity or does it go to negative infinity? Question. In grade 11, this would have been a restriction. We would have said x can't equal 4. And it was just an annoying little thing about rational functions. We didn't really know what was going on. Then in advanced functions, we discovered, oh, when there's a 0 in the denominator that's not also in the numerator and cancels and becomes a whole, when that happens, we end up with one of these vertical asymptotes. That's what happens when you can't divide by 0, is this feature comes in the graph, this infinity. Yeah? Okay. There's many ways to handle this in advanced functions. We probably would have just taken 4.01 and subbed it in, and that totally works. And it's so ridiculously unpowerful that I'm going to sort of ignore it here. By sort of ignore it, I'm going to say, I'm going to get the answer here. I'm going to find out what it is. Here I go. We're coming in from this side. We want a little more than 4, so I'm going to sub in 4.01. Math mode, yes, exit. And then when I hit the fraction button, oh, I get my fraction thing. Did you see what I did there? This calculator acts like both an old style calculator and a new style one. I wasn't getting the beautiful fraction display I wanted, so I switched over to math mode. So I'm going to put in 4.01 in the numerator. 4.01 squared plus 2 times, plus 2 times 4.01 minus 15. And in the bottom, I'm going to sub in 4.01 minus 4. Let me tell you about all the weaknesses of this method. I mean, it may seem awesome. Like, I can see exactly what's going on. I just type my calculator. 1, what if you don't have a calculator? 2, what if the numbers aren't this friendly? And 3, what if these numbers aren't numbers but letters? You know, we're approaching A or something like that. There's all sorts of reasons why we want to be better than just jam it in a calculator. We can get any dummy to jam it in a calculator. We want to be better than this. But it works. We're going to find out whether this is going to positive or negative infinity. It's at 910. It's going to positive infinity. Don't believe me? Try 4.001. That'll be 9,000. You know, so you can get the answer here. I think what I'm going to show you is way, way better. Way, way, way better. And you've seen it. What I'm going to do is I'm going to go limit as x approaches 4 from the positive side, and I'm just going to factor this thing. And what I'm going to do next should ring a bell. Even with online learning and everything like that, we did some of this stuff. Let's talk about 4 plus. We're talking about a number that is ever so slightly bigger than 4. I've already decided it's going to be infinity. The answer is going to be positive or negative infinity. So I don't care anymore about the actual numbers. All I care about is the signs of the numbers. So if I put 4.01, I don't give it a specific number. I just think 4 and a little bit. If I go 4 and a little bit and add 5 to it, do you get a positive number or do you get a negative number? taking 4 and adding 5, positive. If I got 4 and a little bit and I subtract 3, are you going to get a positive or a negative? Positive. So the numerator is positive times positive. I don't need my calculator to do that. And I bet you I can win a race with you. You see the trouble I had typing it into my calculator? Getting in the right mode, typing in 4.01 squared. I bet you I can win a race every time using this method. So it's even faster than using your calculator. And then in the bottom, 4 and a little bit subtract 4, positive or negative? Positive, just by a little bit, but positive. 3 positives. The answer here is positive infinity. Now, where did I get the 2 pieces of information? The first piece of information I got from down here going positive, positive, positive. Oh, it's positive. Do you remember this type of thinking from advanced functions? We set up these grand tables, yeah, and really thought out the individual signs of the factors. Very, very powerful. And then the infinity, I knew right from the start, you know, this was a vertical asymptote, so I knew it was going to be infinity of some type. Okay? Any questions about that? Is this the exact same function? No? 4 from the negative side? Oh, by the way, so I'm going to get my highlighter out back here and go, okay, so I know it's this. That one is the correct one. So if I'm drawing this thing, I know exactly where I'm supposed to go. I'm approaching positive infinity from that side. Now its limit as x approaches infinity. Sorry, as x approaches 4 from the negative side. And again, here's the factoring. And by faster, I mean you should be able to handle these. Once you get what's going on, I'm subbing in something slightly smaller than 4. So that's positive. But the denominator here is negative this time. It's something slightly smaller than 4. So when I subtract 4, I get something slightly negative. I get a negative answer here. And so I'm going to go back to my graph over here. And I know from this side, it goes to the negative infinity instead. I did that a little faster, not to rush things, because I hope you've heard me slow down this afternoon. I did it a little faster to prove that these methods can be done very, very quickly. The fact that I'm doing them slowly on the board, don't underestimate them. Once you get good at them, it's a bang, 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 bang. In fact, the answer might be in your head before you even get a chance to write anything down. You're like, oh yeah, I know what it is. Okay. Oh, I don't need to write anything for this one. Limit as x approaches 4 of this thing. Well, someone in their own words. Help somebody out who doesn't get what the difference is between these 3. What is this asking you to do? Compare the two. This just asks, this is check from the right, this says check from the left, and this is did you get the same answer? And we really, really didn't. In 2 ways, we really didn't. The first level is, well, they're not the same. So that does not exist. But there's another reason, too, that many profs stick to, is that infinity is not a limit. You can't say, oh, the limit is infinity. Really think about that for a second. The limit is infinity? How can infinity be a limit? We use it sometimes because we know what we're talking about. What we mean is, that's where it's headed towards. It's heading towards infinity. You're like, yeah, see, it's fine. It's heading towards infinity. I'm like, oh, yeah? Heading towards infinity? Just think about that for a second. Infinity is not a number. We can't head towards it. You know, like, and you're like, I get what I mean, though. I'm fine. I know what's going on here. Yeah. That's why you see it go back and forth sometimes. But that's not why this one doesn't exist. It doesn't exist because they're not the same. Questions there? More time? Oh, yeah. Okay, this is what I was talking about. Your degree rules will not help you here. You cannot just go, oh, degree of the top is higher than the bottom, degree of the bottom is higher than the top. All those rational function rules are out. But our new weapon does help here. Yeah, so what I'm going to do is multiply this thing by 1 over, oh, I'm not going to give it away. I'm going to let you think about it. Make sure it's clear what you're going to multiply here so that it's the right thing. What is the right one to multiply by here? X to the power of 3, the biggest one you see. That'll make sure that everything there either becomes a number or becomes something over x, which you can handle. Okay? I'll do this a little faster. You let me know if it's too fast. Let's make sure I did it right before I throw it back at you. Doo, 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 doo. I feel great about it. After seeing it this way, I hope you see that this can go a little faster than it did the first time I did. You're really just dividing each term by the x cubed. The reason to do this is because I'm heading to infinity, and this is set up very well to find limits at infinity. For instance, the limit as x approaches infinity of 1 is 1. The limit as x approaches infinity of 1 over x squared, 0. Plus, I've got a problem. I'll come back to that in a second. That cos is the problem here. That doesn't allow me to use my degree rules from advanced functions. In the bottom, 0 plus 0 plus uh-oh. Separate thing about cos x over x cubed. Let's go over here in a big thought bubble. Ready? Limit as x approaches infinity of cos x over x cubed. Sine and cos at infinity can be very troublesome. They go back and forth between 1 and negative 1. It's possible they don't approach anything. The limit as x approaches infinity of sine doesn't have a limit. It doesn't approach one value. It does this. But if it happens to be trapped between two functions, maybe we've got a chance. Here's the thinking. Oh, and here's a better picture right here. I've done that picture twice today already. If I can trap it between two things, life will be good. Here's how you trap it. You start with cosine. You just go, okay, negative 1 is less than or equal to cos x is less than or equal to 1. That's always true about cos. It's a wonderful place to start because it does trap cos between two values. Then I try and get to what I'm looking for. I want cos x over x cubed. So I'm going to divide these all by x cubed. Oops. And I have what I'm looking for, cos x over x cubed trapped between two things. That's not the end of the story. The end of the story is if these limits both head to the same thing. So what I want is limit as x approaches infinity. That's what I'm trying to do, of negative 1 over x cubed. And I want limit as x approaches infinity of 1 over x cubed. And if those two things come out to be the same, that means cos x is trapped between them. And I can get my limit. Getting a flashback from university here. I had a one university class way out in St. Jerome's. It was always at 1:30 in the afternoon, so I'd eat my lunch. I'd walk through the wind and the snow all the way out to St. Jerome's to take this course, and then try and stay awake after being out in the cold. And then, so I spent the whole lesson doing what some of you were doing this afternoon, which is trying to keep my eyes open and just scribble down what the prof said, and then later try and remember what did he say about that again? I can't remember. I tried to write it down, but I didn't. Now with this video thing, later on you can go back and just go right to that example. Fast forward right through on YouTube and go, let's just go over this again. So if this is going well for you, great. If it's not, if it slips out of your brain later, the videos will be there. One at a time. What's the limit as x approaches infinity of negative 1 over x cubed? 0. That's one of the big takeaways of this lesson. This one, 0. And this one, cos x over x cubed, is trapped between the two. So it's got to be between those two answers, between 0 and 0. It's also 0. So cos x doesn't normally have a limit at infinity unless it's being trapped between two other functions, which this one is. What's this called here? What did I make here? Sandwich theorem. It's the perfect name. You make a sandwich out of your Isaac. Yeah. If I just draw, let me know if I'm not answering your question. I think I'm answering your question, but cos x normally does this. And so as we approach infinity, we can't say what it approaches. It approaches everything between 1 and negative 1. It doesn't settle into one value. And those are some extra words to help you with limits. We need it to settle in to one value. All the other ones, as it approached 0, it settled into one value. And cosine doesn't normally do that. However, if we're multiplying cosine by something, or in this case, dividing cosine by something, cosine doesn't look like that. It looks like, do you see this one here? And I'm going to draw a new picture of this to really exaggerate what happens to cosine when it's being divided by x cubed. Okay, so here's cosine doing its thing. And then it's like, oh no, oh no, oh no, oh no. It's being divided by something, and it gets crunched down more and more as it gets in there. Weirdly. Yeah, you can punch this one into your graphing calculator, or maybe into Desmos would be better to really see it getting crunched down. So now it does head towards something. It heads towards 0 because it's being crunched down between the two. Does that help? It could be you're thinking about just subbing in. And in the case of infinity, we're sort of subbing, like infinity's tough to sneak up on, so we're sort of subbing in. Unlike times when we could just sub in the 0 in a previous example, we could just sub into cos, no problem. That was when we had a number, like a 0 or a 1 or a 2. Infinity, when we do this, are we subbing in? No, we're sort of thinking, okay, if I did sub in really big numbers, where is this thing headed towards? And do I know that for sure? And by the way, this isn't rigorous yet. I haven't gone through and proved that this is true. We just know it is at this point of the course. Okay? And maybe it's the infinity that's saying you, oh, can't we just sub in? Not really, not for infinity, because I don't have a specific number I can use. If I could think it through by using bigger and bigger numbers, then that's fine. But I don't have that here. Does that get us closer? Yeah. No, I think you can sandwich a lot faster than this. Yeah? Because look, there's the between negative 1 and 1, and I've gone right to there. So once you've sandwiched a few times, you can slam the bread in there a lot faster and be eating your sandwich a lot quicker. Yeah? All of these things I'm showing you here, I'm showing you how they work, so lots of steps here. When you actually go to use them, they can become pretty fast. He says, won't they always be 0? The examples certainly are, because I'm using sandwich theorem to actually get answers. But there are times when maybe it doesn't work out. Like if it was multiplied by x squared, you could imagine a situation where instead of doing that, because of what it was being multiplied by, maybe as we get closer and closer, maybe cosine does the opposite. Yeah, it gets stretched out by more and more. And then it won't have a limit as it goes in. But the ones we're working on that can be used with sandwich theorem, yeah, they're going to head towards something. But it doesn't have to be 0. It could be 7, 9. These ones happen to come up. Yeah, I would say yes. But as suggested, maybe I'll do sandwich a little faster. A little faster sandwich here, okay? On this one, down here, sine x over x cubed. Maybe you're going to do it like this. You're going to go, okay, here's my restrictions. I'm after limit as x approaches infinity of sine x over x cubed. And I'm going to go, okay, negative 1 is less than or equal to sine x is less than or equal to 1. I'm going to divide those all by x cubed. Limit as x approaches infinity of plus or minus 1 over x cubed is 0. Therefore, limit this is equal to 0. You know what I mean? Like, you see I've done the exact same steps, but that did not take long. Sandwiching does not have to take long if you know what you're up to, right? So I get 1 minus 0 plus 0 over, oh no. Oh, here we go. This is the second of the 3 rules. Actually, I don't know if it's the second one. I don't even know what numbers the rules are supposed to be. There's 3 rules. And a minute ago, 20 minutes ago, I used the rules to find when the degrees were equal. Then I did when the degree on the bottom was higher. In this particular case, the degree on the top is higher. And now we're down to this, 1 over 0. And now we're ready to talk about 1 over 0, finally. After grade 9, 10, 11, 12, now we're ready to really get to the bottom of what 1 over 0 is all about. We can't go 1 divided by 0. Can't. Yeah? Can't be done. You can't go 1 divided by 0. So the odd time in the middle of this explanation, I've convinced people that you can go 1 divided by 0, and that is definitely not true. I've got to be careful what I say to make sure you understand that 1 divided by 0 is out. It's an asymptote. You're not allowed to do that. But when you run into 1 over 0 inside a limit, something specific has happened. It means you've ended up with something very close to 1 divided by something very close to 0. And if you go 1 divided by something very close to 0, let's just punch it in our calculator and make sure we're clear what happens when that happens. If I've got a fraction, and I've got any number on the top, and on the bottom, this number has got very, very close to 0. What kind of number is going to pop up on the screen when I do this? It's a large number. When you take 1 and divide it into very, 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 very small pieces, you're going to get a lot of pieces. So, in a limit, I'm going to give 2 answers here. I'm going to say undefined. Actually, I'm going to give 3 answers here. 1 over 0 is undefined. But for us in limits, that means something very specific. That means positive infinity. Maybe it means does not exist. And maybe now you get why some profs say, no, infinity does not exist. You can't have limit to infinity. But we know what we're talking about when we say limit to infinity. We know what we mean. We mean this, yeah? Right here. Woo! Or woo! Gone. We do understand what we're talking about when we say that. And that's why we put this infinity in brackets sometimes. It's the third of the 3 rules. Equal degree, ratio of the coefficients. Lower degree in the top, 0. Higher degree in the top, infinity. Yeah, all 3 rules I've done now. As x goes to infinity, this function approaches infinity. So whatever it does, it goes up like this. It doesn't settle down into 0 or into 3. It takes off. Sort of like x squared does, yeah? Y equals x squared does this. It takes off to infinity. Good? Woo! Questions? Great stuff. Why is that in the limit and limits involving infinity? We've done two kinds of examples. 1, where we're heading towards infinity. 2, where we end up at infinity. So that's why it's in the limits involving infinity lesson. Okay, use a calculator to evaluate this limit. This limit's a big mess. The things I've shown you can't handle it, but I want to show you how to get your calculator to do this thing. What I'm going to do is go into Menu, and I could go to Graph. Graph would handle it, but the table handles it way better. So if you go to 7 for table, and the 7 for table gives you the same display that Graph does. It says, okay, well, you want a table? Here, give me a function. So the function here is, let me get my fraction button going here. Oh, it doesn't like that. Okay, so I'm going to use divide. X divided by square root x squared. Ooh, I want a bracket there. I feel better with a bracket. Square root x squared plus 7. Okay, and don't press draw or anything yet. Just press execute. So now I've got that function there, x over root x squared plus 7. Now, before hitting, it's awfully tempting to hit the table button. And it's good. It gives you a good result. I like it. But we specifically want the limit as x goes to infinity. So we don't want just any table. We want a table that gives big x values. So just hit F5 for set. And I'm going to set the table. Well, it was about to give me a table that went from 1 to 5, and that's not going to help me to find the limit at infinity. So here I go. I'm going to start at 0 and go up to 10,000. And how much am I going to go up by every time? Well, you don't want a step of 1, because it's going to take forever to get through your table. 1, 2, 3, 4, 5, 6, 7, 8, all the way up to 10,000. So why not step by tens or something like that? And you can play with the numbers and see what works best. Then I got to hit exit to come back here, and now I'm ready to draw my table that goes from 0 to 10,000 with this particular function. And I hit table. Oop, range error. I did something wrong. Let me check the set. 0 to 10,000. Maybe 10,000 is too big for it. Maybe I got to go 1,000. Exit. Exit. Oh. Oh, maybe because I'm not allowed to have 0 in this? 0 squared? No, that's fine. Set. 10. And end at 10,000. Step by 10. Yes. Enter. Table. Ooh, why am I getting a range error? Let's try again, a smaller number. I just did this earlier, so I'm not sure what's happening. Enter. Exit. Table. Oh, there we go. I must have been using too big a numbers. I don't know what's happening there, because I used 10,000 earlier. And look at, even 10's big enough. Look what the y value's doing. 0.9667. But such a great illustration of limits here. As I go to bigger and bigger x values, 999, 9997, 9997, 9998, 9999, 9999, 9999, 9999, 9999. It's a perfect illustration of limits. 999999999, but it never gets there. But in the limit, I've got the answer to the limit. Equals 1, using the calculator. Question? Oh, your set was F1 for, oh no, select. Oh, because you went into graph. Go into table. Now go set, yeah? And I just went 0 to 1,000 by tens. Oh, I know why. I used my own calculator to go 10,000. Maybe this one on the screen. Did anyone have trouble doing 10,000? You did 10,000, it worked? Oh, it crapped out on yours too. Oh, okay. Might have to do with the size of these numbers. Maybe with the one I did, it wasn't squared, so it handled 10,000, no problem, or I don't know what. Okay, so calculator can handle this thing, just building a table. And you can find out some answers and get to know these things a little better. How could we find this limit without a calculator? Oh, interesting. This is really interesting. Okay, let me give it a try. I didn't know this was in this lesson. X over root x squared plus 7. Okay, advanced trick here. Because your rule 1, rule 2, rule 3 aren't going to help you out here. Because the degree of the top is 1, well, what's the degree of the bottom? Square root of x squared? We never really gave that a degree label. So I've got to expand my trick a little bit. I've got to multiply this top and bottom by something that when it gets to this x squared, it's going to cancel it out. Now I know what to do here. I know what to use. And the best I can tell you is to think about what the degree sort of is. The degree of the top is 1. And the degree of the bottom, if it's x squared and then square rooted, its degree is sort of 1. And that gives me the hint I need to try 1 over x. And all seems well for a minute. And then this question's going to blow up in my face. On the top, x times 1 over x is 1. and the bottom, 1 over x square root of x squared plus 1. What a nightmare. And there's two ways to handle this. I'm going to try and bring that 1 over x into the square root. And how I'm going to do that, I'm going to go up here and do it so you can really see it. Incidentally, not a test question. This is beyond this course now. This is really stepping into first year calculus at university now. You know, like this is really reaching out. How I'm going to do that is instead of 1 over x, I'm going to write it in a different way. I'm going to write it as square root of 1 over x squared. Give that a stare and make sure you decide that I haven't broken any rules. I've said, okay, instead of writing it as 1 over x, I'll write it as square root of 1 over x squared, and that allows me to bring it into the square root. And it multiplies by the x squared, and I get 1. It multiplies by the 1, and I get 1 over x squared. And now I'm in the clear. And the biggest reason this example's in there is to prove that this 1 over x squared trick isn't about advanced functions and getting rid of those 3 rules. It's about being able to handle any kind of limit you want. It's got power. Madison. How did I go from here? X times 1 over x would be x over x, which would be 1. And then this 1 over x, I didn't know what to do with, so I just wrote it in front of the square root. Oh yeah, it's definitely not right. That's a 7. 7, 7, and then it does become a 0. I don't think I knew it was going to become a 0, and that's why I ignored it. I don't think that's what happened. That was just carelessness because I was busy explaining. Here to here? All I did was say, I've got to get, if this is going to help me, I've got to get it into the square root. So I need this to be a square root of something. What it is the square root of? It's the square root of 1 over x squared. 1 over x squared. If I square at the top, I get 1. And the square root of x squared is x. Sort of. It is for this one, but it's not always. You know, okay. Good? Beyond the scope of this course, but just an advertisement for this incredible trick, multiplying by 1 over the biggest x power when you're doing infinities, yeah? Questions? That's why I wrote an A here. A lot of the ones we were doing were 1 over, and 1 over something really big is 0, but 7 over something really big is still 0. You know, instead of 0.00001, you get 0.00007, 0. It's heading to 0. Yeah. Good questions? Yeah, that's really, we can't sub infinity in. What we can do is go, what's going to happen as I keep subbing bigger and bigger numbers in? And as I keep subbing bigger and bigger numbers in, this is going to get as close to 0 as we want it to be. You want your answer to be 1.017 zeros with 1? Okay, I've just got to use a big enough number here. That's the power of infinity, is to say, I can use as big a number as I want. So as close as you want to get to 1, I can get you there, which means it's the limit. That's where it's headed if I can get as close as you want to get. Yeah. He makes a great point. He says, you can only do this stuff because of the limit. Yeah, it seemed like no big deal. I'm like, oh, check out this. It's limits. You're like, okay, it's limits. It's when it gets really big. But the power mathematically, it might be the most powerful mathematical force ever found, is to be able to do limits. It changed everything as far as how they could do mathematics in the 1700s. And the result is everything you see today. No exaggeration. Yeah? Yeah, it was bigger than we could comprehend, and we found a way to handle it. Yeah? By sort of not really handling it. But I got to tell you, mathematicians have handled it in the sense that This is all very rigorous. You're seeing the basics of it here now. It all does work. It's like c squared equals a squared plus b squared. In grade 9, we go, trust me, it works. It's really good. And only later do you find the proofs to go, no, it's true. Let me show it to you. But proving all this stuff rigorously challenging. You got a taste of it today with those epsilons and deltas that were, for a second, I was like, whoa, what is going on here? And that's the taste of what it takes to really make this stuff so we are handling it, not sort of handling it. Yeah? Great questions. More questions? How could we find this limit without a calculator? Oh, I did that. I went back, right? See above. Can you use this approach to evaluate this one? And the answer is no. So there's still more to be known about limits. This doesn't have a denominator. So my little multiply top and bottom by something trick is not going to work, and I'm going to need some more tricks yet. And it's really a combination of the tricks you've already seen. But, there's no limit to how far we can go with limits. Yeah? So we'll stick to the ones we've seen so far for a little while. Yeah? I'm only on slide 9 of 16. Okay, well, you know what? I'm going to go for another, if your brain's exploding, I'm going to go for another 10 minutes at least in the hope that I get within range of finishing this lesson. And then we'll see where we're at. Okay, maybe we have to cut it short here to give you some work time. Because give yourself a mark out of 5 on the 2 sets of homework for this section. And this isn't me doing a homework check. This is me deciding what I should do. Give yourself a mark to 1 to 5 on last night's homework. 5 being it's done or pretty much done. I got a couple of questions to ask you. There's one I don't understand, and then 4 being no, I got some work to do, but we're okay. 3 being long way to go yet, and 1 being I didn't know we had homework last night. What? What homework? Okay, just give me a mark on this so I know how to proceed. 3s, 4s, and 5s. Okay, what about this homework on the getting formal with limits I gave you some time with? 5 being I'm done all this stuff. 4 is like, well, I got work to do. Give yourself a number. It's just going to decide how I approach things next. Okay, lots of 1s. Okay, so saw a couple of people give me a finger I didn't expect there. That's how I feel about this homework, Mr. Todd. Okay, so then I'm not worried about wrapping this up early where you can only do some of these. And I'll try and look at that. We'll see where we end up, okay? We'll go one more round. Well, this is fast. A fast sandwich here. Shall we? One more sandwich to make sure we got the sandwich down pat. Here's how sandwich often starts for you. Why did I use sign? Well, it's right there. There's sign in the question. What would you like to do next to get this thing set up for sandwich? Divide everything by x, and the reason I did that now is because I wanted sine x over x. Now find the limits of each piece. Go limit as x goes to infinity of negative 1 over x. That's 0. Limit as x goes to infinity of positive 1 over x. That's 0. Therefore, limit as x goes to infinity of sine x over x. Not 0, you silly rabbit. I've been a parent a long time. I have to be careful not to swear in front of my little kids. So I've got all these sayings that pop up. We call them baby swears at our house. You silly rabbit. That's our alternative. Hey, did that make you feel better about sandwich? The sandwich can be quick. No, shaking your head. Tell me more about, let's go through the steps slowly. When I saw sine, I went, okay, where can I trap sine? Sine is very friendly because it traps nicely. It's got a nice range on it, negative 1 to 1. I divided everything by x to get this. Go, your question. That I should be doing sandwich? Let me rewind and talk about some other situations. When you get 0 over 0 in some of the questions, it's a hint that you've got more work to do. And if the thing factors, you should factor. If it's got a square root, you should rationalize. If it's got cube root, and I saw some people ask me about this and got this far, you should use U substitution. If it's absolute value, yeah. For now, I'll say if it's a limit at infinity, oh, it doesn't have to be a limit at infinity. If it's a limit involving sign and you don't know what else to do, take sandwich for a test drive. I don't really know what, outside of experience, how you're going to know that sandwich. It's not quite as easy as all the other methods. Like writing absolute value as piecewise, it's like so obvious you have to do it. You know, like once you've seen it once, you're like, oh, I'll be ready for that now. Sandwich, not so obvious. Yeah, it's a good question. Other questions about this sandwich? Anybody getting hungry talking about all these sandwiches? You'll double toast your sub at Subway? I feel like such a dope. Like they toast my sub and it's like melted and toasted a little bit, but it's like, it's mostly mushy is basically what I get. And the guy behind me, I'm getting my sub, and the guy behind me says, yes, could I get a double toasted, please? And I watch and they put it through twice. It comes out nice and crisp, and I'm like, you couldn't put that on the sign? You couldn't let me know? How'd that come up? Oh, sandwich. Oh, I'm getting hungry. Getting distracted too. Any other questions on sandwich? Oh, this slide's quick. Properties of limits involving infinity. They're the same properties you saw before. Limits are very well defined, they behave well. You want to break it up and do the limits on the individual pieces and add them later or power it later? This is just permission to do all those things. The only weird one is here. If the denominator comes out to be 0, why, you've got a problem, don't you? Well, we've got a taste of how we might deal with that problem when we get 0 in the bottom now. So nothing too crazy there. That's just permission. It's a sheet of permission saying, instead of needing a trig toolbox or log laws for limits, you just go ahead and do what you would expect you can do. Example, here's me using those rules. This says find the limit as x approaches negative infinity of 4x plus sine 3x over x. A very difficult limit because there's so many pieces to it. However, if I do this, I'm going to do both steps before pausing for questions. This is showing off the power of the limit laws. The limit laws say this thing was a big, scary mess, but I can break it into 2 different pieces if I want and approach them individually. And individually, these limits are much easier. In fact, this one is shockingly easy. And this one is more difficult. What strategy would you suggest for this limit with a sign in it? I think she's literally eating a sandwich. Is that a sandwich? Oh, it wasn't. Wouldn't that have been great if she had been eating a sandwich right at that moment? Have we given it away too much? I don't know. It just takes experience to go, oh, sign, big mess, you know? Now, it sort of looks like this one, though. Hang on. Why isn't it this one? Okay, so now you got to finish memorizing this thing. Maybe earlier you're like, oh, sine of x over x is 1. I'm like, hold on. As x approaches 0. That's true. For infinity, we need sandwich. Here comes my quick sandwich. Negative 1 is less than or equal to sine of x is less than or equal to 1. Here's one that I hope doesn't confuse the issue. Even if it's sine 3x, sine can only spit out things between negative 1 and 1. It doesn't matter if you multiply the number by 1 or by 3 before you start. Sine's only given back negative 1 and 1. Divide everybody by x, and then your 3 limits. Limit as x goes to infinity, negative 1 over x, that's 0. Limit as x goes to infinity, 1 over x, that's 0. So limit as x goes to infinity of sine 3x over x, that's also got to be 0. So I get 0 here. Limit as x goes to infinity of 4. Ooh. No. Except that, yes. I should have wrote that, but no, it didn't matter in the answer. And so I hope you know this is 4. And so I get final answer 4. What time's your break? 1:35? Am I crazy? $1:35. Okay, that's what I'm going to do. I'm going to teach the break, and that's it for the day no matter what. Okay? Then you have the whole last session to try and chip away at this homework a little bit. Slide 12 of 16. It's going to be close. Questions here? Combination of sandwich and obvious limit, but the limit laws allow us to break it apart and do them individually, no problem. More time here? More time, okay. What are the final slides? Oh, this would be a great break. Oh, I could just stop and do end behavior models tomorrow. No, we'll stop there. Okay, that's perfect. Okay, good. Noah. No. No, the ones I've done so far all worked out to 0. So it may, and sandwich doesn't always work. You might try sandwich and these two limits don't come out to be the same thing, or you can't get it to set up. You know, there isn't that many sandwich homework questions, and they're all set up like this. They're just sort of nice. It's like intro sandwich, you know, like nothing too crazy here, you know. Yeah, the one I put in the test is pretty straightforward. I might have even done it today already, or very close to it. You know, like it's really an intro to just let's just get a feel for what sandwich is all about. Not trying to kill you with it at all. Yeah. Other questions there? Okay. It's the perfect place to stop, we believe. We just figured this out at the front. Tomorrow I got to talk about end behavior models. I'll teach that right off the hop tomorrow. So when you get to the homework and it says blah, blah, end behavior model, 2 choices. If you got time, flip back in your textbook and read what it says about end behavior models, because it's not, this is the easiest part of the lesson, I believe. And, but I'll do it right off first thing, and then I'll jump into continuity lessons right off that. Now you'll have your break at 1:35. Can you take your break early? Yes. Early, you can't go late, because then the other classes show up. But you're the earliest break here. I don't know why they chose to do it that way. The other breaks are 2 and 2:05. In fact, going early might help you avoid the grade 11s a little bit, if that's what you want to do. Are we clear then? Tonight, as all you can, folks, dig in. Your week off's coming up, right? It's Wednesday already. You know, you can have your week off coming soon. Let's stick with it here. This set of homework, that set of homework, the questions on the handout here, but not the one in the optional one, yeah? And then limits involving infinity. We can now do all of that except for questions that mention end behavior models. That'll be part of tomorrow. Good? Better, you seem to perk up in the afternoon. Was it the break, or was it optimism started coming along? Yeah, okay.